Okay, I think we'll get started. So last lecture we talked about the 0th law of thermodynamics. This lecture we're going to talk about the first law of thermodynamics, and then the next lecture we're going to talk about the second and third law of thermodynamics. The first law of thermodynamics deals with total internal energy. So total internal energy is just the energy content of a piece of the system due to all the translational, rotational, vibrational motion, the potential energies. We kind of all glom it together into the total energy of the system. So in thermodynamics, we are not at all worried about the fact that the material is made up of atoms and molecules and what they're doing. We only think about the average value across the whole macroscopic thing we can hold in our hands. So collectively, because this is made of stuff, it has some energy content, and that's the total internal energy. Now, we've talked about already that we have the system and the surroundings. So we have the surroundings or the environment, we have the system. So we're referring to the system here. And the first law states that the total change in internal energy is heat lost or gained by the system from the environment, from the surroundings, and work done by the surroundings on the system or work done by the system on the surroundings. And so that constitutes the change in the energy of the system. And what this is this is a statement of conservation of energy of the whole thing, of the system and the surroundings. So we've talked about in Introduction to Physical Chemistry 1, we were talking about systems that were single particle mechanics. We talk about conservative systems and dissipative systems. Here we are talking about this whole thing as a total, and then how does it interact with its environment. And so if we had an isolated system, so one that can't interact with its environment at all, then it's a constant energy system. Q and work are 0. No work is being done, no heat is being transferred. So this is the idea of conservation of energy here. And of course, we want to not do a lot of calculus, but it's often best when working with this to think about just an infinitesimal change in the total internal energy given by an infinitesimal change in Q and an infinitesimal change in W. Okay, well, we have to bring in a definition here, and that is the idea of a state function. And most of the functions we run into are going to be state functions. State functions are quantities or properties, in this case they're going to be the thermodynamic properties, that are independent of the path the system took to get to its current state. So if I've got this glass of water sitting on the counter, the total internal energy of that water doesn't matter if it was taken from the refrigerator or taken out of a boiling pot. Once it's gotten to the room temperature and the current state of the system, then the total energy is what it is, regardless of how it got there. Now, this comes in more so when we're making a transition from one state to another, state A to state B. And there we have, again, independent of how we get there. So the delta U for this is going to be the same regardless of what path we take. And that's a property of a state function. Now, what's interesting is that heat and work are not state functions. It matters what path we take to get somewhere in terms of the amount of work that we do. Not in conservative systems of Introduction to Physical Chemistry 1, but certainly in dissipative systems, which this will encounter, it does matter how you get there in terms of work. Same with heat. So what we have here, we have that although that heat and work are not state functions, but the sum of them is. So Q plus W is. And this is purely a physics thing. Right? So this is ill-posed in a sense in a mathematical perspective. This is a state function on this side. These are not state functions. So mathematically, we would expect this not to be true in general. But thermodynamics is this mix of mathematical rigor and physical observation. Well, here's the physical observation. This is the law. So the law comes from repeated observations that we become more and more confident in. And so the physics here of conservation of energy is what says that these two added together represent a state function, and that state function is equal, they're path independent. They themselves don't represent a state function. They're path independent. So no matter how we go from one state to another, this sum is always going to be equal to the change in the internal energy. All right. Let me just do one quick example of this case. What if state A is equal to state B? Then we have just a circular path. And in that case, the change in state functions are always 0. And these are called thermodynamic cycles. We'll talk about a few of them in this course. But certainly as we go up through the curriculum, these will come back. All right, so that's the big deal about the first law. The phenomenon it's talking about is conservation of energy. The mathematical statement is this. The word statement is the change in internal energy of a system is a result of any heat flow in or out, or any work done on or by. All right, let's do an example. Again, we're not going to be able to really get into a lot of examples because it would require calculus in most cases. But we'll see a few examples and then just try to be satisfied with our first pass through laying down these laws. And then as we go through the curriculum, we'll get more and more deep, be able to have the tools of calculus to help us. Okay, so let's look at constant volume heating. So how we want to read these things is like, okay, well, what do I do here with constant volume? Well, if we've just got this block of iron, let's say, and we're going to heat it, and we're saying it's constant volume. Now, that's a little bit of an approximation. The iron does expand a little, but to a good approximation, the volume is constant. So if the volume is constant, it can't do any work on its environment. So we say the work is 0. That's what we get from this constant volume heating. And so then our change in internal energy is simply due to the heating of the iron. And then we can use the heat capacity equation that we talked about last time and get an expression for the change in internal energy. And at our level, at our general introduction level, we said that the heat capacity is constant. So it is a very soft function of temperature near laboratory conditions. And so if we treat it as a constant, which is to a good approximation, then we have delta U equals C delta T there. All right, well, let's look at another example. Let's look at pressure volume work, constant external pressure, and adiabatic. So here we said constant volume, 0. Adiabatic, what did we learn about that earlier? Adiabatic is when we can do work, but no heat is exchanged. So that is a condition where this guy goes to 0. It's PV work, and so we utilize our ideas of generalized force, generalized displacement to write our work this way, as we've done before. And then since we're constant external pressure, so we have to contrive a lot of cases here, although they are important cases, for us to do this without any calculus. Then any small change here, this is just a constant, so then the change in the change in internal energy is then proportional to the change in volume via the external pressure. Note a special case if we are expanding into a vacuum. Then there's no work done. It's adiabatic as prescribed in this case, and then delta U is 0. So that would be a special case of expanding into a vacuum here where the external pressure is 0. Okay, I'm going to bring up something that I'll just more or less tell you about. We have talked about this before when we were talking about work in its sort of normal physics form of force and displacement, and this idea of maximum amount of work. And so we had this box sliding down the ramp. So if you've forgotten that, maybe go back and review that. The idea there was there is a certain maximum amount of work that can be obtained from the system, and you can always do less work, but you can't do more work. And so if we're doing an expansion here from one volume to another volume, let's say the external pressure was 0, right? Then we would be doing no work. But if we're lifting, we certainly could be pressing against some external pressure, in which case we would be doing work. And the case where this is maximum is if the internal pressure is pressing against that external pressure such that any little back pressure would reverse the process, would start to compress. And just like with the case of the ramp, the box, if we have this reversible process, then we say that the P external equals P internal, and usually we don't write the IN, we just write P, and then we have minus P dV. This would be for a maximum work setting. So we can't say this. This is the generalized force, generalized displacement. This is not generalized force, generalized displacement, because this is not an external variable. But it is equal to P external under reversible conditions only. Now, I say that because we are going to run into something called the free energy, which will be ultra important in understanding chemical equilibrium. And understanding free energy it's important to understand the concept of maximum work. Essentially, free energy is the maximum work that you can get from a system. And we'll come back and talk about that in detail later. Let's just pull some from earlier so we can get some very quick results here. Because of this generalized force, generalized displacement idea, we've calculated the work for charging a capacitor. And let's assume that when we charge those parallel plates, there's no expansion of the volume. That certainly might be the case. And let's assume it's adiabatic. So in that case, delta U would be 1/2 C. Okay, fancy C for capacitance, not heat capacity, and fancy V for the voltage across that capacitor, not volume. Let me just add this here. Let's say let's relax this constraint, and let's just say we have a constant external pressure. So we'll just have the atmospheric pressure. So then we would have minus P external delta V. So let's say those plates did move a little bit. We have a change of the volume that's contained sort of inside that capacitor, and we would have this extra term to account for that volume change. We still stay adiabatic. All right, let's look at the battery. And again, we'll assume adiabatic conditions and constant volume. So this battery is going to work and the battery is not expanding or anything. From last time, or not last time, but a fair bit earlier, we were able to determine that for a battery pushing electrons, the work is negative N, really fancy F, the Faraday's constant. So this is Faraday's constant. Which is coulombs per mole. So 96,485 coulombs per mole of charge. And then the total internal energy change, delta U is this, just equal to the work. Now, delta U, very important. You'll notice as you look at your general chemistry book and your general physics book, delta U will show up, or internal energy will show up, but we're going to quickly get to some other functions, namely enthalpy and a certain type of free energy called Gibbs free energy. And so while we're laying down this, we'll come back to these ideas with those functions. And those are they're more convenient to use when talking about chemical reactions. All right, let me just finish with a few things here. So what have we seen here now? Delta U du is dq plus dw, and we can express now dw as a sum of all the possible generalized force, generalized displacement type works. What we'll often do is we will pull out as special the PV work, and then leave all non-PV work separated out. The reason we do that is in many, many situations, we don't want to care about whether this did flex a little bit, or if this battery changes, or if a cell is moving ions in and out of the cell, if that cell's volume is changing. In a sense, that's not the interesting chemistry that's going on. And so what we're going to do is we're going to define a function where we eliminate this term, the pressure volume term. That's going to end up being both enthalpy and free energy. We'll do that, Gibbs free energy. And then that'll allow us to concentrate on the non-pressure volume work, which is usually the chemical work or the electrical work from a battery, which is what we're generally interested in terms of an applied problem. All right, and so far we've talked about two laws, the zeroth law and the first law. We'll make this table now, and we'll add two more next time. So the statement is transitivity here. So TA equals TB plus TB equals TC goes to TA equals, or implies or means TA equals TC. So thermal equilibrium, even if not in contact. The phenomenon here is transitivity, and the physical property, the primary physical property of the zeroth law is temperature. First law, delta U is Q plus W, work plus heat, exchanged with the environment. Conservation of energy is the principal phenomena, and then the property is internal energy. So this is a good chart to start filling out so that you can kind of get the big picture lay of the land of these laws that we're going through. All right, so next time we'll finish up the laws of thermodynamics.